Greetings to all my physics pals. Paul Lake here with another physics problem solved. And I've got a rotational kinematics problem for you. It's a very simple problem, just a wheel spinning faster and faster. And we're going to be using the rotational kinematic equations for constant angular acceleration. And this is kind of a beginner problem. If you've just been introduced to rotational kinematics, this is a good problem for you to practice on. And so let's read the problem. A wheel is initially spinning at a rate of 2.00 radians per second when it undergoes an angular acceleration of 3.5 radians per second squared. Through what angular displacement does the wheel rotate in 2.00 seconds? Through how many revolutions has the wheel turned during this time interval? And C, what is the angular speed of the wheel at t equals 2 seconds? Okay, very straightforward kind of problem. And hey, here's what I suggest you do. Pause the video right now, try to work this problem yourself, and then compare your work with mine when you're done. Don't skip around too much. I do a lot of teaching during the solution to this problem. And hey, so let's get started. So here's what's given. And now we've got a wheel, so I'll just draw some kind of wheel here. It doesn't have to be a real wheel. Maybe I'll give it some spokes. Maybe it's like a bicycle wheel or something. But it's spinning about its axis, and so I'll show an axis like this. And it's rotating around like this, and it does have an initial velocity of 2.00 radians per second. Okay, and it has an angular acceleration of 3.50 radians per second every second, or radians per second squared. And then it's going to do this for a total time of 2 seconds. Okay, and what are we trying to find? Well, for part A, what is the angular displacement? Through what angular displacement does the wheel rotate? Well, that's a change in angular position is an angular displacement. And then for part B, through how many revolutions? So now this, we're going to calculate this in radians, but this is in revolutions. So we really want the same thing. We want the change in angular position, but this time in revolutions rather than radians. And then for part C, what is the angular speed of the wheel at 2 seconds? So we want the final angular velocity. And to help you out a little bit, I made an equation list and quantity chart here on some scratch paper. These are the equations that we use for constant angular acceleration. And of course, this is our variables: change in angle, angular velocity, angular acceleration, and time. And here are the units we use. Now, keep in mind that change in angular position, angular velocity, angular acceleration, they can all be expressed in radians, or radians per second squared, or revolutions per second, or revolutions per second squared, or degrees per second, or degrees per second squared. I almost never see rotational kinematics expressed in degrees per second or so. So I wouldn't worry too much about that one. But this is what we're exercising, right? This is what we're trying to learn how to use, are these concepts right here, these mathematical models, as we say. All right, so let's get started on the solution. So we have, we're trying to find the change in angle, and look at what we're given. We're given initial velocity, we're given angular acceleration and time, and we want change in angle. Now, which one of these equations is most appropriate for finding delta theta, given what we're given. And I think you'll see that it's this one right here. Because in part C, we're trying to find the final angular velocity. This is the only equation that doesn't have angular velocity in it. So I'm going to use this to solve part A. Okay, and this should look familiar to you because this is exactly what we did when we did translational kinematics. Probably the first thing you did is study translational kinematics, when you started your started physics. Anyway, so I'm going to use that equation. So our change in angular position is equal to our initial angular velocity times time plus 1/2 the angular acceleration times time squared. Please don't call this W. This is an omega. Omega, it's a Greek letter, and this is an alpha right here. Now I try to use the quantity name rather than the variable when I describe these, but although sometimes I take shortcuts, but this is not a W, it's an omega. So I don't know, look that up. Okay, and the thing is, it's already solved for what we're trying to find. So this is pretty easy. Our initial angular velocity is 2.00 radians per second times time plus 1/2 the angular acceleration is 3.50 radians per second squared times time squared. Okay, well this is 4. And this is 4 divided by 2 is 2. 2 times 3.5 is 7. 7 plus 4 is 11. And you can use a calculator if you want to. So this should be 11.0 radians. Okay. One thing to keep in mind, in some books, when they give you the initial angular velocity, you might see it written this way. Just seconds to the -1, because a radian is dimensionless, right? Remember, it's the arc length, which is a length, divided by the radius of a circle, which is a length. So it's a length divided by a length. So length cancels out. Just because it's dimensionless doesn't mean it's meaningless. I mean, a radian is a very specific thing. I like to use radians. I like to keep, I don't like using this, especially for beginners, because this is very confusing. Sometimes you'll see this is written as 3.50 seconds to the -2. And again, I don't like this. It's not intuitive. It doesn't, it's not wrong. It's not wrong, but you have to know that it's expressed in terms of radians. This is not revolutions per second. If you see it like this, it's not degrees per second, it's radians per second. If you see seconds to the -1 power or seconds to the -2 power, this is a way of abbreviating radians per second and radians per second squared. Okay. Let's do part B. Now, one of the things we want, how many revolutions did this rotate through? Well, remember that that's just an angular displacement. Or 1 revolution means you're going through 360 degrees, which means you're going through 2 pi radians, right? So we can take our 11.0 radians and multiply it by a conversion factor. And I want revolutions, so I know that in 1 revolution, the wheel rotates through 2 pi radians. Now, even though radians are dimensionless, they still sort of cancel out, don't they? And so we get 11 divided by 2 pi. And when you do the arithmetic, which I've already done ahead of time, you get a angular displacement of 1.75 revolutions. So in that 2 seconds, it rotated through 1 3/4 revolutions. Okay. All right. And if you have any questions or you think I made a mistake anywhere, put it in the comments. I respond to every comment. And also, if you want more problems like this, more practice, look in the description. There's a link to lectures and lots more example problems I'm building. I'm still working on this actually, and probably will be for a long, long time. But I'm trying to build a big set of documents with lots of practice problems for you to help you learn physics. All right. What is the angular speed of the wheel in 2 seconds? Well, looking at my free body diagram, not my free body diagram, like my equation list, I want the final angular velocity, which is right here. I know what the initial angular velocity is. I know what my angular acceleration is, and I know what time. So these are all given. So this is the best equation to use. So that's the one I'm going to use. Okay, and now we can plug this in. This was given to be 2.00, moving through 2 radians every second, plus now it increases its angular velocity by 3.50 radians per second every second, or radians per second squared, times 2.00 seconds. Notice the seconds cancel with the second squared. We get radians per second plus radians per second. 2 times 3.5 is 7. 7 plus 2 is 9. So we get 9 radians per second. That's how fast it's spinning or rotating or whatever at 2 seconds. Now, we can do this another way. Look at that fourth equation. So I'll just put or. And the reason I like to do this sometimes, if I have time, and if you're taking a test, and if you have time, there's a way to check your answer for part A by using the fourth kinematic equation that says the final angular velocity squared is equal to the initial angular velocity squared plus twice the angular acceleration times the angular displacement. That look familiar? Yeah? Okay. So now I can solve for, I'll do it over here, solve for the final angular velocity is equal to the square root of omega naught squared. So that's 2.00 radians per second. I'm going to square it plus twice the angular acceleration, and then times delta theta, which we got as 11 radians. Okay? So if this answer agrees with this, that means this is probably right. If they all agree with each other, you're probably in good shape. And indeed, this is 4. And what is this? This is 2 times 3.5 is 7. This is 77. 77 plus 4 is 81, and the square root of 81 is 9. Woohoo! Don't even need a calculator. Yeah. All right. So there we go. So that means that this is probably right. And that's how you do these problems. Very, very, very straightforward, very similar to what you did when you did translational kinematics. The main thing you have to do is make sure, just like with translational kinematics, you have to pay attention to units. And notice that when I work problems, I show my units in every single calculation, almost never. There are a few times, like if I have to use a quadratic formula or something, I won't include units with the numbers, but usually I do, because units are a great way to catch your mistakes and helps you understand what it is you're actually doing. All right. Hey, if you made it this far, I want to thank you for watching. Please like, share, and subscribe. Share it with your friends, and share it with your physics teacher, and show them my YouTube channel. And there's links in the description on how to get to Google Documents that your teachers can use. And yeah, I'm trying to build a resource for students and for teachers of introductory physics. So cool. Hey, thank you so much for watching once again. And until the next video, may the net force be with you always. That is all.